First, a quick look at the equation for the Fourier transform. It's a pretty fearsome thing, and no, we are not going to do anything more than what our dear friends in the math department and the computer science department have built into the software we make use of when we do this game. But what I want you to see from this is the following. It basically takes a function that is oscillating over time, like, for example, a sound wave that has been recorded from my voice or from a tuning fork or a bunch of radio stations all playing at the same time, for example. And it takes that what's called time domain oscillating function and comes back with a frequency domain function, it's called. Basically a function that marks, okay, what frequencies went into building that sound wave. Now that's easy enough to say, but it's still a little bit of a fuzzy concept. So let me show you again, using my friend the microphone here and the software, a little bit about how this works. So once again, the tuning fork. Now this time around I'm going to sound it and hold it up to the microphone so it can pick up the time domain function, listen to the oscillations over time. But what I'm going to ask it to do now is to then apply a Fourier transform. And what it will do is come back with, here is the frequency that that sound wave was built from. So here we go. Now what I want you to see is that time domain function oscillating came back with a frequency, and the tuning fork I just used was says to has a frequency of 330 hertz. Okay, it sounds an E note, and that's what the Fourier transform, and here's what the Fourier transform came back with. And so what it did is it listened to the oscillations and essentially came back with, okay, here's a function that marks that frequency. Now the power of this technique isn't with one tuning fork, it's with more complex waves, like you would get if you sounded two tuning forks at the same time. Watch this one. Now, let the system sample the complex wave. You see the wave is has that complex pattern to it. But the Fourier transform picks out the fact that that sound was built from a tuning fork at 330 hertz and a tuning fork at 494 hertz. Rather remarkable how that works. And so as the last example of this, once again, the golden tones. Here are the frequencies that make up my singing voice. La la la. No, it's not one of the stellar singing voices, probably because it has quite a complex pile of frequencies in there. But that is how the Fourier transform gets used. So imagine this. We have that complex pile of sounds from the radio station where it's sounding everything from the 96 to 104 megahertz, like we were talking about a moment ago. I said all of the information of that sound spectrum, that FM sound spectrum, was in there, and this is how we would get it. We would take that complex pile of sounds, all oscillating at their own frequencies over time. We would run them through, mathematically, a Fourier transform. And what would pop out is our FM radio sound spectrum. And I want you to notice that was done quickly. We didn't have to sit there and tune it carefully and draw the response or something. We just simply turn it on, listen, turn it off, calculate it. That is one of the major breakthroughs, was the computer power available to do this with NMR, and because it unlocks a lot of the or gives us a great ability to overcome some of the major problems in NMR spectroscopy. Remember, one of the great problems in NMR is simply the signals are very weak. We see very few nuclei actually undergo the transition every time we put the sample in there. And so we are always fighting concentration problems. One of the ways we overcome it is doing this Fourier transform game. What we do is we put our sample in there, we shine our radio frequencies in, we see which frequencies got absorbed. We do that fairly quickly. Then we wait and do it again, and again, and again, and again. We do this several times. The idea is this: if you have really weak signals in there, and let's face it, this is NMR, we do have weak signals, then every time you do this process, the real signals will grow in strength. But any random noise, like the static in the background of a radio, will tend to cancel out. And so it will leave us with a fairly strong signals and all the high resolution we expect out of NMR. And so this was the key breakthrough, not only in proton NMR. Since it was sensitive, you could do that one continuous wave fairly readily if you had very high concentration samples. But this is the technique that broke open carbon-13 NMR. Remember, carbon-13 is a much less sensitive nucleus. The abundance problem is a real crisis there. It was not possible unless you had isotopically enhanced samples to do much with C13 in the good old days. Once the Fourier transform technique came about and the computer power necessary to pull that off, then suddenly carbon became a routine component of NMR, and the power of the technique really exploded. So finally, I want to show you a couple of details of how we process the NMR spectra. Because what the instrument measures is not really what you see as an NMR spectrum. What it's measuring is a collection of oscillating frequencies. Now, much like the tuning fork here, when I sound the tuning fork, I hear the sound, but over time, I get, the sound diminishes as the tuning fork finally goes silent. It's essentially, I induced it to do a sound, but that sound is decaying over time. In NMR, what we do is we measure what's technically called a FID, a free induction decay, an FID. We put our molecules in the big honkin' magnetic field. We then hit them with our radio frequency energies. We listen to which frequencies are resonating in there, which ones are causing spin state transitions to occur. We listen for those frequencies. That sound, those set of frequencies, is loud initially, we hear it initially, and then it decreases over time. It decays. The induced frequencies decay fairly quickly. And so we listen to the FID, it decays, and then we do it again and add the two results together. Do it again, add that result in, do it again, add that result in, and keep doing this a number of cycles until we get a set of raw data, the FID, that contains all the spectral information. It's much like that pile of radio frequencies, that pile of radio stations. It's a mess to look at. Here's what it looks like. This is an actual free induction decay. It's a proton spectrum free induction decay. And then mathematically, we get the software to basically perform the Fourier transform. There's lots of software that will do this. We use here a program from Advanced Chemistry Development, and here's a little bit of the screen that does that. Notice there's a button labeled Fourier transform. You click that, and the free induction decay gets transformed into the actual spectrum. The time domain oscillating function becomes the frequency domain that marks the frequencies of the various peaks. Contained in that information is the fact that some of those frequencies are louder than others. That is where the integration information comes from. It's a remarkably great technique, powerful technique that relies hugely on computer power.